Since the tangent plane approximates a surface S at AB, the equation of the tangent plane yields what we call the linearization to S at the point AB. And it is written as L of xy is equal to f at AB, right? So that's a z value, plus fx at AB times x minus a plus fy at AB times y minus b. If you compare this to the equation of a plane that we just came up with, basically here you have your z and on the left and a z naught on the right, and then the rest of it is just, instead of x naught, y naught, we have a and b. As another piece of vocabulary, we can say, thus the linear approximation or the tangent plane approximation to f at the point AB is f of xy is approximated by what we just wrote down. The f at AB plus fx at AB times x minus a plus fy at AB times y minus b. Now you may be looking at this saying, you just wrote the same thing down twice. Yeah, we did. Here's what we're saying. That a linear function here, which is the tangent plane, is what we're calling a linearization of the surface. The idea is if you zoom in close enough to anything, it's going to look flat. If you're not sure about that, think about what we live on. But that flat surface is not exactly the surface, right? The tangent plane is not exactly the surface. And so linearizing it gives us something that approximates, right? So fxy is approximately equal to the expression that gives us the tangent plane at AB. This is exactly akin to what you would have seen in first semester calculus if you have a curve and a tangent line. At a point, you'd say, well, yeah, near the point of tangency, the tangent line approximates the curve. And it was a linear approximation then. Here, we have a plane that's a linear approximation to a surface. Well, let's see what this looks like in action. First, we're going to explain why the function is differentiable at a given point and then find a linearization at that point. Our function is f of xy is equal to the square root of xy, and our point is 1, 4. F is differentiable at 1, 4 because it's a root function whose domain includes 1, 4. You do get to simply declare that, I couldn't decide what color to use, root functions, radical functions, rational functions, trigonometric functions, polynomial functions, logarithmic functions, and exponential functions, and algebraic combinations of these. That is, if you add, subtract, multiply, or divide them, or compose them, are all differentiable on their domains. That on their domains bit is important because, trigonometric functions aren't always differentiable because they're not always defined, right? Like the tangent of pi over 2. But pi over 2 isn't in the domain of the tangent function, right? This is why I said f is differentiable at 1, 4 because it's a root function. I didn't just leave it at that, whose domain includes 1, 4. That's going to be good enough for us. Well, at this point, you've seen the formula. You know what we're doing. I'd like for you to pause the video and find L of xy for this function at 1, 4. Well, I started with some partial derivatives. Fx at xy is equal to y over 2 times the square root of xy, which simplifies it. We're going to substitute, so it doesn't really matter, but the math voice in my head said, let's go ahead and simplify it. So 1/2 times the square root of y over x. And likewise, the partial with respect to y at xy is 1/2 times the square root of the fraction x over y. Evaluating those at 1, 4 gives us that fx at 1, 4 is 1, fy at 1, 4 is 1/4, and then we're also going to need a z at 1, 4, and so z at 1, 4 is 2 because it's the square root of 1 times 4. Putting this together, L of xy is 2 plus 1 times the quantity of x minus 1, right? 1 taking the place of a, and 1 plus 1/4 times the quantity of y minus 4, where 4 is playing the role of b. Simplifying this equation gives us that L of xy is equal to x plus 1/4 y. I said simplifying this equation, and what we really did was we simplified the expression on the right-hand side. This isn't really an equation, right? It's a function of x and y, and it's defined by x plus 1/4 y. But what did we just find, though, really? This is a linear approximation to the function f. In other words, f of xy is approximated by x plus 1/4 y near the point 1, 4, 2. Now, for a visual idea of what we've just done, I've loaded this into GeoGebra, the 3D graphing tool, and I have here the surface z equals the square root of xy. And here I have the perspective that I tend to draw from, where the x-axis is coming down a little bit to the left, and the y-axis, the positive y-axis, is coming down a little bit to the right. But this doesn't really help us see the surface very well. So what we can see here is got two kind of wings for this surface. Now the point of interest is 1, 4, 2, and let's see where that is. So we see that that's on this surface here. And then the equation of the tangent plane is going to be z equals x plus 1/4 y. Well, now this is an equation, isn't it? Because it's z equals and then some variables rather than a function. Anyway, if we see that, then you can see that the tangent plane does exactly what you expect it would at the point of tangency.